In this video, we'll be reviewing trajectories 3, numbers 2, 3, and 4. Let's start with problem number 2. In this problem, there's an animal on one side. And we know the distance to that animal, and we also know the time to that animal. That'd be the t total in the air. Since the distance is measured horizontally, that would be dx. Now, in order to go that far, although it's not stated in the problem, we know it must take an arcing trajectory. So the initial velocity must be both out of Vx and up of Viy. To find the velocity at the start then, both Vx and Viy will need to be found. Let's start with Vx, which would be the sideways portion, that part of the overall velocity. Since dx and t are already known all the way to the animal, it would simply be a matter of dividing dx by that total time. Well, the x direction turned out to be pretty easy. Let's deal with Viy. Now the Viy portion is the upward speed, that leg of the triangle at the start, if you will. Now, in order to find Viy, we want to incorporate the acceleration due to gravity. Let's go scroll down the page a little bit and consider all of the different givens that we have. We have t total. But one of the problems with using t total to find Viy is that Vfy is downward at the point here where we know the time. It would be much easier if Vfy were 0 like it is here. Well, luckily we can find the t there also. The t to the top would simply be t total divided by 2. So we've got t to the top available to us now, and conveniently, since t to the top comes at the spot where the object is going to stop moving up and start moving down, we also now know that Vfy at that time is 0. And of course the reason it slowed down in the first place is because of the acceleration due to gravity that occurred. With those three variables, we can find Viy. It would simply be a matter of taking negative ag times t to the top. Now, once we've found Vx and Viy, in order to find the overall velocity, we'll have to use the Pythagorean theorem and a little bit of trigonometry. Let's give ourselves a little bit more space and show you how that's done. Vx, the sideways velocity, and Viy, the upward velocity, form a right triangle whose hypotenuse is the overall velocity of the object. Finding that velocity is now simply a matter of taking the square root of Vx squared plus Vi in the y direction squared. Be sure to find that entire quantity before taking the square root. The launch angle here, theta, is an important part of the answer, since velocity is both speed and direction. That launch angle can be found by taking the inverse tangent of the quantity Viy over Vx. Be sure your calculator is in degree mode if you're putting in the angle in degrees. Alright, let's take a look at problem number 3. In problem number 3, we've got a motorcyclist who's going to jump over a big row of cars, and our question is, How many cars? 1, 2, 3, well, how many is it? Of course it depends on how far he can jump. So we need to find dx, how far sideways he can go. Now, since the launch velocity is given 60 meters per second and a launch angle of 12 degrees is given, the very first thing that has to be done is to break that Vxy into its components, how much speed is up and how much speed is out. Recall that in order to find Viy, it's the sine of the launch angle multiplied by the initial velocity in the xy direction. Recall that in order to find the sideways component of the velocity, take the cosine of the launch angle, in this case 12 degrees, times the initial velocity at an angle. That should give you about 12.47 meters per second up and about 58.6 something meters per second sideways. Now, time in the air can always be found if you start with this launch angle and overall velocity in the xy direction from the Viy. And you can see that we've done that here. Now notice that we've doubled it. Now the reason we've doubled it is because that finds t not just to the top where Vf is 0, but the t back down to the ground. Now that equation then has a very specific purpose. That equation only works if the landing is at the same height so be careful not to use it in situations when that's not true. Now we find out that the motorcyclist is going to be in the air for a little over 2.5 seconds. So now you can see here we solve for the sideways distance with dx equals vx times t. This vx, 58.688 meters per second, came from taking the cosine of the original launch velocity. And now that we have the time, we'll multiply them together, and we find that he goes about 150 meters. Now, we want to know how many cars he can get over. In order to figure out how many cars he can get over, we have to take a look at that dx, and then the car length is really 2.1 meters per car. So if you think about it, car. Meters divided by meters per car would really just give us cars. And 149.25 meters divided by 2.1 meters will give you that number of cars. Remember, you've got to cut off any decimal. He won't make it over any portion of a car. That would be the car he lands on. So round down, even if it's larger than 0.5. Alright, 3 is taken care of. Let's take a look at number 4, and then we'll wrap up. Now in number 4, the question is given, what angle is best if you want to launch something the maximum distance? Well, clearly 90 degrees would be terrible. If you shot something straight up, it would go up to its maximum height and then just come straight back down. Now, if we're imagining that you were shooting things from ground level, shooting at an angle of 0 degrees would be similarly terrible, because as soon as it came out of the gun it would start to fall down and be on the ground, and so it wouldn't go anywhere either. Now if we tip the gun up from horizontal or sideways from vertical just a little bit, let's say 20 degrees or so, the one that shot 20 degrees from vertical wouldn't go quite as high as it did when it was shot vertically, because it traded some of its Viy for some Vx. The one that was shot at 20 degrees above horizontal starts out shallower and would get to that same spot quicker without going as high. Now if we went, say, down 30 degrees from vertical, started it out like this, it would go less high than the shot before, and it would go further again. 30 degrees above the horizontal would have a little bit more time in the air, and would land in the same place as 30 degrees sideways from vertical. Well, of course, if you keep taking an angle above horizontal or sideways from vertical until you meet in the middle, what you meet at is an angle of 45 degrees. And in fact, without air resistance, that is the best angle to launch at if you want the object to go as far as possible. No other angle will match it. For every other angle, say 50 and 40, or 30 and 60, or 62 and 28, for every other pair of angles that adds up to 90 degrees, though the projectiles would get to the same exact spot, but the one launched at the higher angle would simply spend more time in the air and go slower sideways as it got to that identical spot. Now, you can calculate this and prove it to yourself. Let's take a look at an example that we did at 30 degrees and at 60 degrees. The answer, of course, is that 45 degrees, you get the maximum amount of Vx and Viy. One thing that's interesting to think about is that the sine and cosine of 45 degrees is both 0.707, the square root of 2. And if you take any other angle, the one that gets smaller of sine and cosine gets much smaller than the other one gets bigger pretty quickly. In any case, let's show you how two angles, in this case 30 and 60, that both add up to 90, end up hitting at the same place. So we took a launch angle of 30 degrees with a Vxy of 10 meters per second and broke it up. You can see Vx is 8.6 meters per second, Viy is 5 meters per second. Found the total time in the air and found dx, and it goes about 8.8 meters. Then we did the same thing at 60 meters per second, or excuse me, at 10 meters per second, but this time at a much bigger launch angle, 60 degrees. This time it's Vx, that's 5 meters per second, and Viy, that's 8.66 meters per second. The time in the air is much larger, but because the object is going slower sideways, the distance remains the same. This holds true for any pair of angles that add to 90 degrees. Alright, a little summary. In number 1, you had a distance sideways and the total time in the air. Now this problem will be much like the tennis ball lab tomorrow and Wednesday. So be sure to know how to do this problem so that you can be successful in the tennis ball lab. In problems like this, it's not uncommon to work back through the trajectory so that eventually the initial velocity at the angle can be found. In problem number 3, that initial launch angle and Vixy was given. In that case, they need to be broken apart into their components of Viy and Vx, and then how far the object goes or how much time it spends in the air can be found from those component pieces. And finally, if you're trying to chuck something a long way in the air, throw it at a 45-degree angle. Thanks for watching.